Sometimes the Regents likes to ask questions about dilations, and dilations with a scale factor of, we'll just call it n for this situation. So you've already seen like side lengths of triangles and like perimeter, for example. The new figure would be n times bigger than the original because it's a one-dimensional measurement. We've talked about area in terms of dilations before. The area would be n squared times bigger. So like if the scale factor was, say, 3, the area would be 9 times bigger than the original because it's a two-dimensional measurement, so you raise it to the second power. And likewise, since volume is a three-dimensional measurement, you would raise it to the third power, and the volume is n cubed times bigger than the original. So like again, if our scale factor was 3, you could do 3 cubed, the volume would be 27 times bigger than the original. Now, strategy for the Regents. I say make a simple example. Try it out and test the final answers. Give yourself different numbers too. So like rectangular prism of 2, 3, and 4, that gives you a volume of 24. If you double it, scale factor of 2, you'd get 4, 6, and 8. You get a volume of 192. Divide these two things. 192 divided by 24 is 8, which is what you expect because that would be 2 to the third power, 8 times bigger. All right, in this example, we have a child-sized swimming pool that's a cylinder. The diameter is 6.5 feet long, and the height is 1 foot. However, we've only filled this pool 2/3. So 2/3 of its height. So essentially what we're talking about here is the height is not 1 foot. The height is 2/3 of a foot. Because that's how far the water goes, because we're trying to figure out how much water is actually in the pool. Now, in order to do that, we need the formula, volume equals pi r squared times the height. So first off, we're given the diameter, so we need to find the volume, or the radius rather, as well. So from that, not 6.5, cut that in half, 3.25 feet. So the problem we're actually going to be solving here is pi times 3.25 squared times 2/3. And then we put that in the calculator and we get about 22 cubic feet of water. So in this problem, Tim has a rectangular prism, length of 10 centimeters, width of 2 centimeters, and we don't know the height. In the other rectangular prism, he has a length of 5 centimeters, same height. So that's helpful, because we can just use the same variable for that. And the volume will be the same. So we have to find the width. So let's plug in the stuff we know. It's length times width times height for this. So the first rectangular prism, we know that we have 10 times 2 times whatever the height is. And this should all equal 5 times the same height times some width that we're trying to figure out. Now this is weird. It seems like we have two unknowns, but in only one equation. So how could we solve this? Well, one helpful thing is that the heights are the same. So essentially we can just divide that away and cancel them out. So if we divide by h on this side, those cancel. Divide by h on this side, those cancel. And we're left with 20 times 10, or sorry, 2 times 10. The whole time it's been 2, not 20. Maybe I was skipping ahead in my mind on this. So with that, we get 20 equals 5 times the width. Divide that by 5, and we get that the width is 4 centimeters.